This is part 4 of a series on Word2Vec. In this video, we'll learn about Huffman trees. This video was produced in Korean and translated into English, and the voice was generated using text-to-speech. In this 2013 paper, Tomas Mikolov et al. Implemented Word2Vec models that use hierarchical softmax to learn from huge corpora. Hierarchical softmax uses a Huffman binary tree on the corpus vocabulary to reduce the training computation of standard softmax. Huffman trees assign short binary codes to frequent words, and this further reduces the number of output units that need to be evaluated. In this video, we'll first learn about Huffman algorithm and Huffman tree, and in the next video, we'll look at hierarchical softmax using this. Now let's look at Huffman codes. In this video, we'll explore Huffman codes, which are described in Chapter 4 of this book. The Huffman code is an algorithm used for lossless data compression developed by David A. Huffman in 1952. A common way to represent a file is to use a binary code. In such a code, each character is represented by a unique binary string called the code word. There are two ways to use code: fixed-length binary code and variable-length binary code. A fixed-length binary code represents each character using the same number of bits. For example, suppose our character set is ABC. Then we could use 2 bits to code each character as follows. If a file contains a character string like this, each character is encoded using the given code as follows. With this encoding, it takes 18 bits to represent the file. The other is a variable-length binary code. We can obtain a more efficient coding using this code. Such a code can represent different characters using different numbers of bits. In this example, we can code one of the characters as 0. Since B appears most frequently in this string, it would be most efficient to code B using this code word. In this case, we cannot code A as 00 as in the example above, because we cannot distinguish between 1A and 2Bs. Furthermore, we would not want to code A as 01, because when we encountered a 0, we could not determine if it represented a B or the beginning of an A without looking beyond the current digit. No code word for one character constitutes the beginning of the code word for another character. For example, if 01 is the code word for A, then 011 could not be the code word for B. So we could code as follows. This way, we need not look ahead when decoding the file. With this encoding, it takes only 13 bits to represent the file. It is not hard to see that this is optimal, given that it is the minimum number of bits necessary to represent the file with a binary character code. These binary codes can be represented by a binary tree whose leaves are the characters that are to be encoded. To decode, we start at the first bit on the left in the file and the root of the tree. We sequence through the bits and go left or right down the tree, depending on whether a 0 or 1 is encountered. When we reach a leaf, we obtain the character at that leaf. Then we return to the root and repeat the procedure, starting with the next bit in sequence. Given a file, our goal is to find a binary character code for the characters in the file, which represents the file in the least number of bits. Let me give you an example. Let's say our character set is A, B, C, D, E, F, and each character appears in the file the number of times shown in this table. This table also shows 3 different codes we could use to encode the file. Let's compute the number of bits for each encoding. C1 is the fixed-length binary code. This code requires 255 bits to represent the file. C2 is one of the variable-length binary codes, and it requires 231 bits to represent the file. C3 is another variable-length binary code, and it requires 212 bits. We can see that code C2 is an improvement on the fixed-length code C1, but C3 is even better than C2. The binary trees corresponding to codes C2 and C3 can be expressed as follows. The frequency of each character appears with the character in the leaf nodes of the trees. As we'll see later, C3 is optimal. The number of bits required to encode a file using a binary tree T corresponding to a given code can be expressed by the following formula, where VI is the set of characters in the file. Frequency, VI, is the number of times VI occurs in the file. And depth, VI, is the depth of VI in tree T. Looking at this optimal tree, characters that appear more frequently are placed at shallower depths, while less frequent characters are placed deeper in the tree. There is an inverse relationship between the frequency of a character and its depth. Our goal is to find the optimal tree like this. This is the Huffman code. Next, let's look at the Huffman algorithm for creating a Huffman tree. Huffman developed a greedy algorithm that produces an optimal binary character code by constructing a binary tree corresponding to an optimal code. A code produced by this algorithm is called a Huffman code. Let's go through this algorithm step by step with an example. In step 1, count the frequency of each character in the file. In step 2, sort the characters in ascending order of the frequency. These are stored in a priority queue PQ. The character with the lowest frequency is given the highest priority. In step 3, remove these 2 highest priority characters from PQ. Let's call this P and this Q, and create an empty node R. Then assign P to the left child of R, and assign Q to the right child of R. And set the frequency of R to 15, which is the sum of the frequencies of P and Q. And then insert the node R back into the priority queue. Then the priority queue becomes like this, In the next step, remove these two nodes and combine them as we did in the previous step. And then insert this new node back into the priority queue. The frequency of this node is 27, which is 12 plus 15. Since this value is greater than 25, this node is inserted at the end of the priority queue. Then the priority queue becomes like this. In the next step, the characters A and D are combined like this. Repeating this process produces the following Huffman tree. Assign a 0 to every left branch and a 1 to every right branch. The sequence of zeros and ones along the path to a character's leaf node becomes its unique prefix code. A can be coded as 00, and D can be coded as 01. To decode a compressed bit stream, we traverse the Huffman tree using the bits in the stream. Starting from the root, a 0 bit means moving to the left child, and a 1 bit means moving to the right child. When a leaf node is reached, the corresponding character is identified and appended to the output, and the traversal restarts from the root for the next character's code. Next, let's write the Python code to create a Huffman tree. We use Python's priority queue class to implement an ascending order priority queue for Huffman coding. Let's implement the pseudocode we looked at in the previous slide in Python. The user-defined data type on the right node type can be written as a Python class as follows. The variable symbol represents each character in the file, and the variable frequency represents the number of times the character appears in the file. These two variables are the left and right branches of this node, and we write a less than operator to compare the frequency variable between this and other nodes. This operator is used later in the priority queue class. Next, we write the Huffman algorithm in the pseudocode on the right as Python code as follows. This algorithm has been explained in detail in the previous slide, so I will skip the code explanation. Our character set used in a file is as follows, and the frequency of each character is as follows. Now let's construct a priority queue for Huffman coding. Create an empty priority queue. Create a node containing each character in the character set and its frequency. And insert that node into the priority queue. Next, we use this priority queue PQ to create a Huffman tree. The generated Huffman tree is as follows. Root.frequency is 85, and root.left of frequency is 33. Root left.left is a leaf node, and the symbol and frequency of this node are A and 16 respectively. Next, we traverse the Huffman tree to find the code for each character. Starting from the root node, we recursively traverse the tree until we reach all leaf nodes. The results are as follows. This matches well with the results from the example in the previous slide. In this video, we looked at the Huffman algorithm and wrote code to create a simple Huffman tree. In the following video, we will implement a simple skipgram model using hierarchical softmax based on this tree.